Good evening, engineers. So, welcome to our first YouTube live session powered by Chevin Academy. So, I really appreciate you guys for joining us. So, if you've not subscribed, I implore you to subscribe to the channel. So, we are going to be starting the worked example on design of Flip Slab in the next few minutes. So, if you have any question during the course of the lecture, you can write it down in the comment section. So, I'm going to look at it after I've made the presentation. So the introduction to this course have already discussed about design of RIPS Lab, an introduction where I explain what RIPS Lab is all about in its entirety and also give some design criterion that you have to fulfill before you'll be able to design a RIPS Lab according to either the Euro code or the BS code. So in this live session, we want to look at an example. So if you've not watched that video, you can check some of my last video, my last two videos. So you can check it on YouTube. I'm sure you are going to get it. So this live session is just going to cover the work example. That is, we are going to take a sample RIPS Lab and then we design it uh, and then we provide adequate checks that are necessary as a structural engineer. So as I've mentioned, kindly subscribe to the channel if you've not, and then you can also join our membership program. With this membership program, we have a lot of items in which that are really interesting, where we provide detailed design videos and also other aspects of structural and civil engineering. Thank you. So the first thing we want to talk about is the work example we want to look at. So this is a typical RIP slab. The size of the RIP slab is 5 meters by 8 meters, and this RIP slab is supported by beams and columns. So we understand the reason why we have RIP slab majorly. Um, so the reason is just because when our normal solid slab, when it is the span of the slab is getting larger and the normal solid slab is no more economical for use, then we tend to apply rip slab. So the idea behind the rip slab is we all understand that concrete is very good in compression but poor in tension. So and then we know that in reinforced concrete, the main purpose of the reinforcement is to provide the tension that are not available in the concrete itself. So what rip slab try to do is we remove the tension parts of the concrete where there is tension, where we need to provide tension. We remove that part and then we replace it with a much more lower construction material. So that is why you can see some roof slab can either be with hollow blocks or with ordinary solid blocks, and then we now provide ribs in between these blocks. So this is one form of rib slab. Another form is when there is no hollow blocks at all. So we just have the rib beams and then the topping slab. So this is a typical example. So in the other form where there are blocks, the blocks are not really considered in design because based on the code, we have some requirements for the strength of blocks. But generally in design, practically, we used to neglect it, assuming that those blocks are not contributing to the strength of the slab. So generally in the design of rip slab, the hollow blocks are technically neglected as if they are not there. So this is example we want to look at. So we want to look at, like I've mentioned, is a slab with dimension of 5 meters by 8 meters and then supported by beams. The primary beam are beam O1, as you can see on your screen. And then we also have some beams in the horizontal direction, beam O2. So the primary beam are the main beams that are taking the rib beams. So the first thing we want to establish is the slab parameters. So if you cut a section along the span of the rib beam, this is what you are going to see. This is the secondary beam. This is the other beam. This beam is not really supporting the rib slab, the rib beam itself. So the span of 8 meters along the strip that we cut, this is section 2. So the slab we want to look at has this dimension. So these are the dimension of the slab. The slab size is 5 meters by 8 meters. The rib spacing is 500. So based on what we assume here, you can see it from the diagram. The rib spacing is 500 mm. According to the code, this rib spacing must always be less than 1.5. So because it is less than 1.5, that means the requirement for rib spacing is satisfactory. Then for the rib size we are proposing 125 by 250. Based on the code, the minimum depth of your rib beam is 125. So sorry, the minimum width of your rib beam is 125. So we are going with a rib beam size of 125 in width and then 250 in depth. Then the slab topping is 50 mm. So based on the section, I can show you. So this is the section of the rib. You can see that the spacing, the center to center spacing is 500. The topping slab is 50. And then the size of the rib beam, the depth of the rib beam is 125. The width of the rib beam is 125. The depth is 250. And then the in spacing is 375. So in case of hollow blocks, your in spacing must be spaced in such a way that they accommodate the hollow block you want to use, or whatever type of block, either solid blocks or hollow blocks. Or in some other countries, they make use of red bricks. So depending on the material you want to use. But as I've mentioned earlier, the blocks is not really considered in design because we assume that it is not contributing to strength. That is the much more safer assumptions to make. So, and then lastly, the slab topping, as I've mentioned, according to the code, the slab topping should be between 50 mm and the clear spacing divided by 10. The clear spacing here is the spacing between your rib. Based on the dimension we have here, the clear spacing is 375. So whichever is greater between 50 mm and 375, 375 over 10. So 50 mm is greater. So that is the minimum topping. So, but because we have a topping of 50 mm, it satisfies the minimum requirement. And then the rib depth should be the rib depth we assume excluding topping. You know, the total rib depth, including the rib beam and the topping, is 50 mm, 250. So excluding topping, we subtract topping of 50 mm. So we have 200. So this rib depth must be less than twice, must be less than 4 times the width of the rib beam. And the width of the rib beam in this case is 125. So that means your rib depth excluding the topping must be 4 times 125. So that will give us 500. So that means the maximum rib beam that you can use, rib depth, excluding the topping that you can use, when the width of your rib beam is 125, is 4 times the width, which is 500. But because in this case we are having 200, so that means it meets the requirement. So based on the dimension of our slab, it satisfies all the requirements in terms of the minimum size and the maximum size as given in BS 8110. I hope I'm clear. So if you have any question, you can drop it in the comments based on these explanations. So now that we've established the slab parameters, the next thing we want to do is to estimate the load. So in this section, we are only going to be considering the dead loads, the permanent load. So we consider only the dead loads and the life load. So the dead loads in this case is we have two structural components. We have the slab topping, we have the ribs, and then this is a slab. We need to cater for finishes and partitions. So for the slab topping, the thickness of our topping is 50 mm. So we convert it to meters. So that will be 0.05, what we have here. So that will be 0.05, what we have here. Then multiply by the spacing between the ribs. That is the spacing of the center to center of the ribs, which is 0.5. If you recall, we use 500 mm. So convert it to meters, we have 0.5. Then you multiply by density of the concrete. So the density of concrete here, we are assuming 25 kilonewton per meter cube. So if you multiply all this, the total weight of your topping is going to be 0.6 kilonewton per meters. Then we've calculate or we've estimate for the topping. The next one is the rib beam. So the rib beam, the size is 125 by 250. So you convert this size to meters. So 125 is 0.125. 250, which is the depth, is 0.25, and then multiply by the density of concrete, because the rib is made of concrete, reinforced concrete. So at the end of the day, we have 0.75 kilonewton per meters. And then we have the finishes and partitions. So for finish and partitions, uh, generally we assume, as design engineer, so what we assume here is 2 kilonewton per meter square for finishes and partition across the slab. But because what we want to design here is, we only want to design the rib beam, because the main component here is the rib beam. So multiply by the spacing between the rib beams, which is 0.5. So you have 1.0 kilonewton per meters. So the total load, the total dead load in this case, is just the summation of all the loads, the topping plus ribs plus finishes and partition. Then we also have the live load. This live load depends on the occupancy, whatever purpose is your rib slab is used for. We know that rib slab is used for low and medium live load. It's not really advisable for heavy live load like warehouse. So we assume an office purpose of use, that is for office building. So a live load of 2.5 is assumed, 2.5 kilonewton per meter square. So when we multiply this by the spacing between the center of the ribs, which is 0.5. So at the end of the day, we have a total live load of 1.25 kilonewton meters. And then finally, we calculate the design load. The design load is just the ultimate load, applying factor of safeties to the actual loads. So for dead load, we apply a factor of 1.4, 1.4 times the dead load plus 1.6 times the live load. So this is going to give us 5.29 kilonewton per meter. So what we calculate here is the load on one rib of the rib slab. So 5.29 kilonewton per meter per rib. For one rib, this is the load we are going to have on it based on our geometry. So now that we've estimated the load, the next thing is to analyze. So if you have any question based on this load estimation, you can drop it in the comment section. After the presentation, I'm going to attend to them. So the next thing before you analyze, actually, for beams in the code, we have something we call the effective span of a beam. So when a beam is simply supported, you can see that from the example that I gave, our rib slab is a simply supported slab. Simply supported in the sense that there's no other slab attached to it. The slab is just 5 meters by 8 meters. No slab to the left, no slab to the right, no slab above it, no slab at the top. So because of that, we can consider it to be a simply supported slab, or a simply supported slab. So, but if you refer to clause 3.4.1.2 of the code, so the code gives some guidance on calculating the effective span of a simply supported beam. So, because our rib slab, we are designing the rib, so it's as if we are designing a beam. So that is why we have to apply this approach. So a typical rib is going to be 5 meters long, because the rib is along the 5 meter span of the beam. And then the supporting beam is 225 by 600, 225 by 600. This is just section 1 that we cut on the layout. So what the code says is the effective span of a simply supported beam should be the span. Span in this case is the center to center distance. So in this case, our center to center distance is 5 meters. So the lesser between the span and the clear distance plus the effective depth of that beam. So the next thing is we need to know what is the clear distance. The clear distance is the distance from the in to in of the beam. That is from this support, the distance from here to here. So this distance is the clear distance, CD. So the minimum between the actual span and the clear distance plus the effective depth is going to be the effective span of that beam. we need the effective span in order for us to analyze the beam to get the moment and the shear force. That is why we are doing this. So definitely the effective span, we need to know our effective depth first. The total depth of the beam is 250. So to calculate the effective depth, we need the height of the beam, 250, minus cover to reinforcement. So we are assuming a cover of 25 in this case. Then minus links, in case if there is links, it is a rib. So it's like a beam. So in that case, all the reinforcement are tied down with a link. So the 10 centimeter, 10 here is the links, and then half diameter of bar. The bar we are assuming is 16 for our rib beam, but in the design we might end up with something lesser, but let's assume 16 half of it. So at the end of the day, your effective depth is 207 millimeters. So now to apply the effective span, so the effective span will now be the lesser between 5 meters or the clear distance. The clear distance is calculated from the center to center distance minus the size of the support. In this case, the size of the support is 0.225. So 5 meters minus 0.225 plus the effective depth using this formula. So effective depth is 207, but we convert it to meters. So we have 0.207. So at the end of the day, our clear span, effective span is 4.48, 4.98. You can see that this value is approximately 5 meters. So in a practical design, this step is usually ignored because between 5 meters and 4.98, there's really no much difference. So you can just ignore it and use 5 meters in your analysis. Then the calculation of the effective span for a continuous beam is a little bit different from this. So if you want to know more about that, you can check out our course on flat and rib slab design. So I leave the link in the description of this live session. You can check it. So you are going to see the design of every different scenarios of rib slab that we have and their detailings. So now that we've been able to calculate the effective span, the next thing we have to do is to analyze the rib slab and then to determine the effective flange of width. This is the reason why we need to calculate this effective flange width is because our rib slab is like a T-beam. So we have to design it as if we are designing a flange beam. So that is why we need to calculate this. So to analyze it, because the rib beam is a simply supported, so we can use WS square over 8, the design formula, to analyze the beam. We know our W from second step, then we know our L from the last step that we just calculate now, the effective span, which is 4.98. So and then divided by 8. So this is going to be the ultimate design moment for the rib slab. Then to now calculate the design shear force, the design shear force is calculated because this is simply supported. So that is WL over 2. But in this case, our L is going to be the effective span, which is W is 5.29 from the loadings, 4.98 from the effective span divided by 2. So we end up with 13.17 kilonewton. So now we've analyzed the beam. We've already know our bending moment. We know our shear force. The next thing now is to do the design. But in the case of the design, we need to evaluate what we call the effective flange width because we are designing the rib slab as if it's a beam because the main component there is the rib beam. So rib beam with topping slab. So in that case, we need to evaluate the effective width of flange beam. So to calculate the effective width of flange beam, you can refer to a course in the you can refer to this course in the BS code 3.4.1.5. So I don't want to be showing us all those in this live session so that it will not be too lengthy. So you can refer to this clause 3.4.1.5. But if you want to see full detailed explanation, like I've mentioned, you can check out our course that I had in the description of this video. So this course explains everything. So it shows you every part of the course and then what the clause says in the code and then how to apply it. But this video, we are just going to be applying it. So the code says for the effective width of flange beam, you must take the lesser between this formula and the actual flange. The actual flange is the center to center distance between the rib. And based on our assumption, we assume that 500 is the center to center distance. So that means whichever is lesser between this formula and the actual flange. So that means at the end of the day, we substitute BW. BW is the width of our beam, the rib beam, which is 125. Remember, our rib beam is 125 by 250. So 125 plus LZ. LZ is the effective span that we calculate. So 4980 divided by 5 and 500. So at the end of the day, this expression gives us 1121 millimeters. But the actual span that we assumed was 500. So based on the code, we take the lesser. So we go for 500. So I hope this is clear. So if anything is not clear here, you can leave a comment. I'm going to attend to all the comments. So now that we finished step 4, we've been able to analyze the beam. The next thing we have to do now is to now design for the reinforcement. So we are going to go for the bending moment first. So for the bending reinforcement, we need some parameters that we have to establish. The first parameter is BF, that is the width of the flange beam, which is what we've calculated to be 500 in the previous slide. Then we have the effective depth. We've also calculated this one to be 207. And then we have the FCU. FCU is the characteristic strength of concrete. This is based on your design mix, whatever concrete strength you want to you think is possible for you to achieve on site based on the mix ratio you want to have. So for this exercise, we are assuming 225 Newton per millimeter square. And then the next parameter is the Fy, which is the strength of your reinforcement. You know, this is reinforced concrete. We are designing the reinforcement for the tension part. So we assume Fy of 410. So our design moment is 16.4. So we all know this formula, we are familiar with it, m over bd square FCU to calculate your K. So substitute m of 16.4 here, substitute BF of 500, substitute effective depth of 207, and then FCU of what, 25. So if you do that, you are going to get a K value of 0.31, 0.031. We all know that if you get a K value less than K prime is 0.125. What this means is your section did not require compression reinforcement. You only require tension reinforcement. Tension reinforcement is sufficient. So from there, you can now calculate your Z. Z goes by this formula. I believe we all should know the formula. D into brackets 0.5 plus square root of, I believe we all know this formula, so that is why it's not added in the slide. 0.25 minus K over 0.9. So what you just do inside there is you substitute your D 207, you substitute the calculated K 0.031. At the end of the day, you have Z, which is what we've calculated here. So once you are done with this, you just substitute it inside the area of reinforcement, area of tension reinforcement, AS. So substitute moment 16.4, but you convert it to Newton per millimeters. That's why you multiply it by 10 to power of 10 to power of 6. You convert it to Newton per millimeter cube. Then 0.95, Z is 199.61, Fy is 410. So what is left here is just substitution. So at the end of the day, our rib beam require a reinforcement of what? 210.94 millimeters square. This is the area of reinforcement required. So to design for the bending reinforcement, you now provide for your reinforcement. So you can either do two things. What we want to do here is we want to provide a reinforcement area that is higher than what we calculate. So you can either go for T12, two number of 12 mm reinforcement. If you go for two number of 12 mm reinforcement in one layer, sorry, this is in one layer, you are going to arrive at this area, 226.2. So 226.2 is slightly higher than 210. Or you provide two number of 16 mm in one layer. This one is going to give us an area of 402.1. So practically, I will advise you to go with two number of 16 mm because the area is much more heavier compared to 210. But you know, in rib beams, in rib slabs, our rib are always very small. In this case, the rib size is 125. So we need to know if the spacing between this reinforcement is enough to pour during casting of concrete. So that is why we do this simple calculation. So this simple calculation is the size of your rib beam, the width in this case 125, minus cover. The cover is the cover you apply to the left and to the right. So let's say this is our beam, and then this is the link reinforcement. So this link reinforcement hold your tension reinforcement together. So this is 2y16 that we provide, 2y16. So we want to know if the spacing between this reinforcement is enough to hold the concrete. So that is why we do this calculation. So the cover here is cover here. This is cover to the left hand side, and then cover to the right hand side here. So because we have allow a cover of 25 to the left and right, making 50, and then you subtract the diameter of your reinforcement. We have two numbers, so that is why we have 2 times 12. So the total spacing is 51 millimeters. So for this spacing to be adequate, it must be greater than the aggregate size plus 5. So aggregate size depend on the size of aggregate you want to use, but the common one is 19 mm aggregate. So if you go with 19 mm aggregate, so that means the spacing between your reinforcement should be 19 plus 5. So that is around 24 mm, or let's say 25 mm in this case. So 51 is greater than 25 mm. And then if you are using 16 mm reinforcement, so instead of 12 here, you replace it with 16. So you have 43. 43 is also greater than 25. Definitely, your spacing of reinforcement is adequate. During casting of during casting, you are not going to have issues in terms of the aggregate size to enter into the space between the reinforcement. This simple calculation here is important for detailing. So now that we've been able to establish the bending reinforcement, the next thing is to now check for the shear reinforcement in the design of rib slab, and that is going to be step 6. So if you are just joining us, if you are not yet subscribed to this channel, I will advise you to please subscribe and also plead, because this is what is going to help the channel to grow more, and so that we can consistently make live sections that educate us engineers like this. So for shear reinforcement design, the most popular code in the BSC 210 for shear reinforcement is clause 3.6.4. Here you see everything the code recommends on shear reinforcement design. So for we need to establish our design shear force first. Based on their analysis, we have 13.17 kilonewton. So definitely from here we can calculate our shear stress. Shear stress is force over area. So and then the area is going to be the width of the beam and the depth of the beam. But in this case, it's going to be the effective depth. So that will be force is 13.17, but it is in kilonewton. We convert it to newton. So that's why we multiply by 10 to the power of 3. And then we have 125 times 207. That is the B is 125, D is 207, just substituting. So we have 0.31 Newton per millimeter square. So if in terms of shear reinforcement, we have about 3 to 4 categories in terms of shear reinforcement design. Most of the time in rib slab design, shear reinforcement are not really required. Especially if the spacing between your ribs are not too wide, so you might not need to provide shear reinforcement, but the code recommends some recommendation. So what we are doing here is we want to check if we will need to provide it or not. So the shear stress on the rib slab is 0.51. We now need to calculate the capacity of the concrete to resist this shear. So if the capacity of the concrete is enough to resist the shear, then we don't need to provide any reinforcement. But if it is not enough, that is when we now provide reinforcement. But before we check for that, the code says that the ultimate shear on any concrete section must always be less than this 0.85 FCU or 5 Newton per millimeter square. So whatever the minimum between these two, if your section, that is, if the shear stress we calculate here is greater than this ultimate shear, what that means is that section is not sufficient in terms of shear. But if it is less than it, it is sufficient, and then you can provide reinforcement if the capacity cannot take it. I hope you get. So this is the ultimate shear for that section. So if we use 0.8, our FCU in this case is 25. So square root of 25 will give us 5. So 0.8 times 5 is 4. So between 4 and 5, the code says the minimum. So the minimum is 4. So that's why here the ultimate here is 4 Newton per millimeter squared. So to now calculate, since our shear stress 0.51 is less than this, so that means we can proceed. But if it is greater, what that means is we can't proceed. We need to go back and adjust the section. So we can adjust the section either by adjusting the size, the width, or adjusting the depth. Either one we do. So now that this is satisfactory, the shear stress is less than the ultimate capacity, we now need to determine our concrete shear capacity, the capacity of our concrete against shear. It is given by VC. So if you go to this clause, you are going to see a table where you can calculate VC. But to make it easier, you can use this formula. This formula is quite straightforward. So 0.79 times 100 AS. AS here is the area of reinforcement you provide. We provide T216. So that means our AS is going to be 402 based on the area of reinforcement. And then B, we know what B is, 125. We know what D is. D is 207. Multiply by h power 1 over 3. Multiply by 400 over D, h power 1 over 4. Everything divided by gamma. This gamma is usually taken as 1.25. If you check this clause, you are going to see the detail. So if you make this computation, you are going to end up with a concrete shear capacity of 0.86. So based on this, you can see that our shear stress is also less than the shear capacity. You compare these together. So that's why we have shear stress V is less than shear capacity VC. So based on this, there is no need for us to provide shear reinforcement. But the code says that in terms of rib slab design, it is recommended that you provide uh, links. In this case, they did not call it shear reinforcement. They call it links reinforcement. The purpose of this is to hold your tension reinforcement in place. The T216 that we provide in the bending reinforcement to hold it in place so that it will satisfy the cover requirement, and then during casting you not have issues. So that is the reason why. And the code recommends that you can provide that in space of 1 meter or 1.5 along the rib beam. So that's why we said here that provide 8 bar at 1 meter spacing. So this one is just to hold the design reinforcement, the tension reinforcement together. So that is the main purpose of this link reinforcement we provide T8 at 1 meters. So now that we've been able to check for shear reinforcement and we know that it is not required, another important thing that you need in a rib slab design or waffle slab design is to check for the deflection. You know, our slab is 5 meters by 8 meters. So if you want to go by solid slab, you might either end up with maybe a thickness of 175 for it to pass. So here now we need to check for deflection. This is one of the important things that we have to do here. So check for deflection, we are still making use of 8110, and the clause here is 3.4.6.3 to check for deflection. So we need to establish the span of the rib beam. The span is 5 meters, which is 5,000 if you convert it to millimeters. And then your BW, the width of your rib beam, 125. BF, you know, it's a flange beam. We are designing it like a T-beam. So BF is 500. 500 here. You establish your moment. We know how we calculate this. And then your D is 207. So the first thing we want to do is we want to know the, in terms of deflection, we have two methods of calculating deflection, either to the Euro code or to the BS code. So the first method is using the span to depth ratio. You calculate your span and then you divide it by your depth. That ratio, you now compare it with a limit that is given in the code. So if the actual is less than the limit given, let's say what you calculated is 20 and then the limit given in the code is 30. So the actual is less than the limit, therefore deflection is satisfactory. That is the basic span effective depth ratio. The second method is using rigorous calculation. So this one is not really it's not commonly used, especially in practice. So most of the time, we stick with the effective span ratio, especially if your beam is not too long. So if your beam is not too long, you can make use of this actual depth effective span ratio. So if you look at most design textbooks, this is what you see. So if we need to establish our actual L over D, our span is 5 meters, our D is 207. If we divide it, we have 24.15. So this is the actual ratio. So your limiting must be greater than this for the deflection to be satisfactory. So let's go. But for you to do that, we need to establish what we call BW over F. The reason why we are doing this is because our rib slab is like a T-beam. So based on the code, we have two sections. If you check table 3.9 of BSc 210, you see that we have two sections, rectangular section and flank section. So for flange section, you need to know if this ratio BW over BF is less than 0.3 or greater than 0.3. So if it is less than, like in our own case, BW over BF is 0.25. If it is less than, you use the value in the table. But if it is greater than, then you interpolate. So if you want to know how to do that, like I've mentioned, everything is explained in the course Rib Slab design and detailing. You can register for the course using the link in the description. So just click on it and then register. Then you see everything um that I'm trying to explain, but not in a much more detailed form. You see it there. So because our BW over BF is less than 0.3, so we can use the value of the table directly. That is the meaning. So from the table, the basic ratio for a flange beam, and two things are involved in order to select the basic ratio. You need to know the continuity of your slab, if the type of support, if it is simply supported, continuous, or cantilevered. So for a simply supported, the basic ratio is 16. So that's why we pick 16 from table 3.8. But this basic ratio, based on the reinforcement that we provide, this one is only for unreinforced concrete. But because we provide reinforcement, we need to modify this factor due to the addition of reinforcement, the tension reinforcement that we calculate. So we need to modify this factor. So to modify it, we need to calculate what we call the service stress, Fs. So this is given by this formula 2 times Fy. We know what Fy is. As required, the area of tension reinforcement required, divided by 3 times area of tension reinforcement that we provide. So substituting Fy is 410. The area we calculated is 210.94 for the tension reinforcement. Then the area we provided is 402. Just substitute. Beta here is taken as 1 most of the time. It's taken as 1. So we got 143.4. Then another thing you also need to calculate is M over BF D squared. So this M over BF D squared is another factor. We have a table where you read this against this, or you can use the formula. So I didn't write the formula here, but the formula is 477 minus Fs over 120 into 0.9 plus this equation. So let's say this equation is z plus z. Then you now must plus 0.55. This is the formula. You can either use this formula where you substitute Fs that we calculate here, and then you substitute M over BF D squared here. So whatever you got is going to be your modification factor, MF here. Or you use the table. We have a table, I think table 3.10. where you read Fs against this. So either one you want to use. So at the end of the day, we get a MF value of 2.2. So this 2.2 must always be less than 2. The maximum modification factor, MF is modification factor. You know, I told you this basic ratio is for unreinforced concrete. But because of the addition of reinforcement, we need to modify the section. So we need to modify the section. So that is why we have 2.5. So that's why we have the multiplication factor. So we calculate 2.2 based on the code. You can't use more than 2. So if it is greater than 2, what you will use is 2. So that is why here we now say the limiting is basic ratio times times the multiplication factor. Basic ratio is 16, multiplication factor is 2, then you have 32. So this is our limiting, the maximum ratio. So, but what we calculated, the actual ratio is 24.15, which is less than this. So that means deflection is satisfactory. I hope this is clear. So now we've been able to design for the rib beam. We've designed the tension reinforcement. We've checked for the shear. We saw that is not required. We also checked for deflection. We see that it is satisfactory. So the only thing that is left now is the topping slab. The topping slab most of the time is usually provided using mesh reinforcement. You know, the thickness is 50 mm. So it will be difficult for you to arrange conventional reinforcement. Let's say you want to use 10 mm bar. You need to allow for cover at the top and at the bottom. You arrange your reinforcement in the first layer, you arrange reinforcement in the second layer. You see, at the end of the day, it will be it will not look good. So at the end of the day, you might need a thickness more than 50. So that is why generally, to save costs and also for practicality, it makes sense more to make use of wire mesh. So but the code recommends that topping reinforcement for slab, you can see that in clause 3.6.6.2 of BS 8110. So if you take the course, we are going to explain everything. This is just a short explanation. So we have the AS required. The code says you should take 0.12 times the thickness of the slab, the percentage of it as the area of reinforcement. So that means we have 0.12 times the height of the topping. The height of the topping is 50 mm divided by 100 times the area of the slab. But you know, in slab design, most of the time, we usually do per meter run because this wire mesh as well, they are in per meter length. So you multiply it by 1 meter. So that's how this 1 meter come about. So at the end of the day, we get 60 millimeter square per meter length. So to now know the mesh you have to pick, the code also give us spacing limitations. So the spacing of your wire mesh should be the maximum spacing should not be less than the rib spacing divided by 2. The spacing between your ribs divided by 2. That is the maximum spacing you are going to pick. So our rib spacing is 500 divided by 2, we have 250 millimeters. So in order to select the mesh you can use, the code for that is BS 4483. This BS here, but I've attached the table here. So we have different kind of mesh. We have structural mesh, square mesh, long mesh, and warpings. So the common one are the structural mesh, the one that we have here. We have A98, A142, A1. Let me try to zoom in a little bit. So we have A1, A98, A142, A193, A255, A9. So the first thing here is the size of the mesh. So all these size mesh their space are 200. Remember, based on our design, the maximum spacing is 250. So we can go for this square mesh because the spacing between the mesh is 200. So the next thing is the area, the cross-sectional area. The number after the A is the area of the section. So A198 means a wire mesh with an area of 98 millimeter square per meter length. That's the meaning. A142 means a wire mesh, a square mesh of 200 by 200 with an area of 149 millimeter square per meter length. That's just the meaning. And then you can see that A142 has a size, that is the diameter of the mesh is 5 mm. A198, sorry, 5 mm. A142, 6 mm, like that. So that's how we come about this. But because our required area is 60, so we can just go with the smallest one, A198. So now we've completed the design from step 1 to step 2. We've been able to design for the tension reinforcement, we've checked for shear, we've checked for deflection, and then we've provided wire mesh for the topping reinforcement. So, but the last step we are going to be doing is the detailing. So here we want to detail the slab. So I think some people in the comment section are asking us to provide a sketch. So I think you are going to see the sketch here. So, but let us talk about the rib beam first. This is the section of the rib beam. This is how the rib beam is going to be, 5 meter long. Based on our design, we specify 2T16 at the bottom. You know, if you can recall, we only require tension reinforcement. So that means for a simply supported member, the tension reinforcement is only at the bottom of the section. So 2T16 at the bottom, which is what was required based on the design. But because of the link reinforcement we are providing, we need to have something that will hold it at the top. So that is why I said you can either go with 2T16 or 1T16. So if you go with 2T16, this is the shape of your reinforcement. This is the shape. But if you go with 1T16, this is the shape in which your reinforcement will follow. So if you use this shape or this shape, either of them are correct based on the design. Like I've mentioned, the only important one is the bottom reinforcement here, 2T16. The top reinforcement is not required in design. It's a compression reinforcement, it's not required. So you can either go for 2T16 or 1T16. For economic purpose, you can go for 1T16. But whichever one you want to go for. So this is how the detailing will go. And then this is going to be the section of the rib beam, of the rib slab at the end of the day. So you have your topping reinforcement of A90, A98, and then we have your topping slab of 50 mm. This is the reinforcement, wire mesh type A98, area of 98. And then for your rib beam, you can provide 2T16 at the bottom, and then at the top, you can go with 2T12 or you go with 1T10 or 1T16. So you can go with either of these shape, either shape A or shape B, whichever one is correct. So based on your choice. So this is how you can design for a rib slab. So this is how you can design for a rib slab in according to BSA 2110 and also according to the Eurocode. So and then I've also show you the detailing part. So I believe we've understand this. So if there's any question, I'm going to wait for maybe like 5 to 10 minutes. If you have any questions, you can leave it in the comment section now. I will see it immediately and then give a response. So we have someone is asking if where we can find the wire mesh, the mesh table in the code. The mesh table is not in the code. I told you you can find it in BS 4486. That's where you can find it. But to make it easier, you can check detailers manual. So under detailers manual, you are going to see the mesh table. And then if you want to have all the presentation and also study part, we have, so you can take the course. So if you take the course, you have the BS code, the detailers manual, the presentation slide that I use, everything will be given to you. So someone is asking, my question is on the use of polystyrene to replace clay pot. Is there any change to consider? Like I've mentioned, when you remove some part of the concrete in rib slab or waffle slab, those whatever you replace it with is not considered in design. So you can use any material of your choice. So far it satisfy uh it is suitable. Yeah, let me just put it like that. So far it is suitable. So if you use polystyrene, it's okay. If you use clay pot, it's okay. If you use hollow brick, is okay. If you use solid bricks, is okay. Anyone you decide to use is okay. I hope you understand. So I have 4 minutes left. Any question, you can ask your question in the comment section and then I will respond. Thank you to Engineer Damilari. Thank you as well. Okay, I have less than 3 minutes. If you came late, I'm sure you'll be able to rewatch it. So it's not something you can miss. You can rewatch the video on YouTube. It will be available. Okay, I have less than 2 minutes left. So thank you everyone for joining this session. I really appreciate your time. So as I've mentioned, if you are interested in our course, you can check out the link in the description of this video on Slab, and you can also check out other courses on reinforced concrete design, detailing, and all of that. So and then you can also contact us for your project. We also handle design and then we provide consultancy services as well. So thank you for your time. I believe with this explanation, you have a little bit insight on Rips Lab design. We have other situations in Rips Lab. The one we designed here is just a simply supported one. So lastly, let me answer this question last before I go. Someone is asking that, can we use 3Y12? Yes, you can use 3Y12 instead of 2Y16. But the problem there is the spacing. So our width of the beam is 125. So if you want to arrange 12 mm, three number of 12 mm, the spacing between the ribs, it will be around 19 mm. That will be the spacing between the rib. When you remove cover, you remove links, you remove the diameter of your reinforcement. So the spacing will be too small for you for casting. So if you want to do that, what I will advise is you can use 4y16, 4y12 in two layers. That is, you have two layer at the top, then you leave a spacing of maybe 25 mm, then you provide another two layer. So you can do it like that. I hope you get. But if you want to use 312, it will be advisable to increase your width to maybe 150. I hope that is get. Yes, you can add that. Adilo brick not dead load. You can see that from this design, we didn't consider the hollow bricks. So it's not considered in this particular one. Like I told you, you can have hollow brick or without hollow brick. So you can put it or you can't put it. This design is based on the assumption that it's not there. But when it is there, it is not really contributing to strength. But you can add the weight. You can add the weight yet. It's not a problem. So thank you everyone. I think our time is up. So I hope to meet you in another section, and I believe you are going to get the course. I believe that. And if you didn't get it, I'm sure you get another one. Thank you. See you next time.